2009 Canadian Open Mathematics Challenge, Part B. In the diagram, angle CAB is 90 degrees, AB is 9, and BC is 15. Determine the area of triangle ABC. Well, first we're going to probably need this distance from A to C, so we can figure that out pretty quickly with Pythagoras. So if that is x, we have x squared plus 9 squared is equal to 15 squared. So that means that x squared is equal to 225 minus 81, and therefore x squared is equal to 144. X is 12. All right, so x is 12. Now to figure out the area of triangle ABC, area would be 1/2 base times height. The base is 9. The height we just calculated is 12. And that looks like 6 times 9, which is 54. So there you go. Part B. From Part A, triangle ABC has side BA extended to D. If the area of triangle CDB is 84, determine the length of CD. Okay, so they are saying now that this is equal to 84. So 1/2 base times height. The base from A to D, I'll just call that y. So the base looks like 9 plus y. And then the height, I just figured that out in the previous question, right? It was 12. So that's 12. And then they told me this area is 84. So 84 is 1/2 times 12 is 6 times 9 plus y. So that's my equation. Divide through by 6, and that would give me 14 over here, 9 plus y, and therefore y is equal to 5. And what did they want? They want CD. Okay, they want this side. Okay, so I've got to do Pythagoras. So that means that CD squared is equal to 5 squared plus 12 squared, if you use the Pythagorean theorem on that triangle. And that's 25 plus 144. So that's 169. And therefore CD is equal to 13. In triangle PQR, PQ is 25, QR is 25. If the area of triangle PQR is 300, determine the length of PR. So PQ they're saying is 25. QR is also 25. And anything else they tell us? Just the area is 300. And then P to T I'll call H. So 1/2 base times height, the base is 25. And the height I have called H. They're saying that is equal to 300. So that means that 12.5 H is 300. And therefore H is equal to 300 divided by 12.5 is 24. Okay, so this H is 24. All right, so where do we go from here? I think if I draw a altitude to here, so I'm going to try to make that perpendicular. Yeah, so this is another altitude, so that's a right angle. Okay, that should help me, and that I will just label as H2. It's also an altitude. And then, since this is an isosceles triangle, this side is equal to that side. When you draw a perpendicular, it will cut the base into 2 equal segments. That's the rule. So each of those equal segments I will call X. All right, so now I can figure out the area using this as the base and this as the height. So the area would be 1/2 base, which is 2x, times height, which I have called H2. So the area is 300. So therefore 300 is equal to x times H2. Okay, and therefore 300 over x is equal to H2. And then I'm going to have to figure out my value of x. And I think I can do that using Pythagoras on this triangle right there. So I wonder if this h was even necessary, but in any case, it doesn't matter. So x squared plus h2 squared is equal to 25 squared. X squared, h2 is 300 over x, all squared, is equal to 625. So multiply through by x squared, and you'll get x to the power of 4 plus 300 squared is equal to 625 x squared. So if I put everything on one side, it'll be x to the power of 4 minus 625 x squared plus 300 squared. Now at this point, you've got a choice. You can use a quadratic, but I think I can factor this. I'm pretty sure x squared minus 400 minus 225, and that should work. So that means that x squared is either 400 or x squared is 225. And therefore x would be 20 or x would be 15. And therefore they want the length of PR, so PR is 2x. And it would be, that means either 40 or 30. And that's it. Triangle PQR has vertices 7, 13, 19, 1, 1, 1. If 4, 7 is the midpoint of PR, the midpoint of PQ is N. Determine the equation of the median of the triangle that passes through points Q and M. All right. I don't think it has to be a work of art, so let's just draw a basic diagram. And then let's label this now. So we got 1, 1 here, 1, 1, and that's R. And then 19, 1, so somewhere here, and that's Q. 19, 1. And then we have 7, 13. So somewhere here, that's P. So we connect those like that. And then they are telling me what? That M is the midpoint of PR. So PR, so the midpoint is right here. So M, 4, 7. And then anything else? And PQ has a midpoint N. So N. And then we can easily figure that out with the midpoint. 19 plus 7 divided by 2 would be 13. And then 13 plus 1 divided by 2 is 7. So there you go. Okay, so now that it's labeled, let's go to A. Determine the equation of the median of the triangle that passes through points Q and M. Q and M. So they just want me to figure out that line's equation. Okay, that shouldn't be a problem, I think. So we got to just figure out the slope. So that's rise over run. So that would be Q and M. So 7 minus 1 over 4 minus 19. So that's 6 over minus 15. And in lowest terms, that's negative 2 over 5. So the equation is y is equal to mx plus b of any line. M we just figured out is minus 2 over 5x plus b. And therefore, now we just have to figure out b. We can substitute any of these points, either M or Q. So either one, I'll just put in the 19, 1. So when y is 1, that means x is 19. So that means we have 1 plus 38 over 5 is b, and therefore b looks like 5 over 5, 43 over 5. So that equation looks like y is equal to minus 2 over 5x plus 43 over 5. That is part A. Okay, let's keep going here. Part B. Determine the coordinates of G, the point of intersection of Rn and Qm. Okay, so the point of intersection of Rn and Qm. Okay, so there's Rn. Right there. So that point they're saying is G. This point right here. All right, so obviously I'm going to need the equation for Rn. All right, so that shouldn't be a problem. The line, this line here That was the equation of QM. So all I need is the equation for Rn. Rn. All right, so what are the points? 1, 1, and 13, 7. So again, same sort of story. The slope, rise over run, 7 minus 1 over 13 minus 1. So that looks like 6 over 12, which is a half. Okay, so y is equal to mx plus b, so m is a half plus b, and just substitute either of these points. I'll just choose that one. 1 is equal to 1/2 1 plus b, so b is equal to a half. So therefore that equation is y is equal to 1/2 x plus a half, right? So now to get the point of intersection, we just have to take this and set them equal to each other. So minus 2 over 5x plus 43 over 5 is equal to 1/2 x plus 1/2. So 43 over 5 minus 1/2 is equal to 1/2 x plus 2 over 5x. And then, you add these fractions and get a common denominator. Multiply top and bottom by 2, multiply top and bottom by 5. So this is 86 minus 5 over 10. Here, same thing, top and bottom by 5, top and bottom by 2. So 5x plus 4x over 10. So that looks like 81 is equal to 9x, and therefore x is equal to 9. So if x is equal to 9, substitute that into either one of these equations. Let's put it in this one. And that means y is equal to 9 over 2 plus a half. So it'll be 9 over 2 plus a half, and that looks like 10 over 2, which is 5. So the point G looks like x is 9 and y is 5. So 9, 5 are the coordinates. Moving right along, point F is on PR, so that QF is perpendicular to PR. Point T is on PQ, so that RT is perpendicular to PQ. Determine the coordinates of H, the point on the intersection between QF and RT. Okay. All right. I think, should we, I'll just use the same diagram. I don't think it should be too messy. I'm just going to draw those perpendiculars, so I'm not even sure how it's going to look, but I'm going to make that one. It doesn't really matter if it's not super accurate. And then the other one, I'm trying to make them perpendicular, right? So how about that? Okay, that's good enough. So that basically means that these are right angles. Yeah. Okay. And obviously I need some space, so let's move it over. Okay, so let's label this. This they're saying is F. This point right here, and this point they're saying is T. So they are saying that these two meet, and obviously they meet right here, and that is your H. And I've got to find the coordinates for H. Okay, it shouldn't be a problem. All right, so first of all, I've got to figure out the equations for RT, right? This is R and this is T. So that line. And then I've got to figure out the equation for QF, where this is Q and this is F. Okay, so RT, I've got the points 1, 1, and T, I don't have the T value, the coordinate, so I've got to try a different approach. Okay, so here's the approach. RT, this line, is perpendicular to this line. So that means that slope will be a negative reciprocal. So the slope of PQ, the m value, if you remember, did I calculate it somewhere? I think I did, right? PQ. I don't think I have. Okay, not a problem. I can do it. PQ, let's see, it would be 13 minus 1 over 7 minus 19. So that looks like it's 12 over minus 12. So that's negative 1. So the slope for RT would be the negative reciprocal of negative 1, which is 1. So therefore that equation would be y is equal to mx plus b, and that m I have already figured out as 1. And then since q is on the line RT, I can put that in, which is the coordinates 1, 1. So 1 is equal to 1 times 1 plus b, and therefore b is 0. So the equation of RT is y is equal to x. Okay, that's nice. That's a good start. And in the same way, we'll figure out the equation for QF, and then we can figure out the point of intersection. QF is perpendicular to PQ. So PR, P to R. So PR, I have to figure out its slope. So that's going to be 13 minus 1 over 7 minus 1, and that looks like 12 over 6, which is 2. So therefore, the negative reciprocal, which would be the slope for QF, and the negative reciprocal of 2 is minus a half. Okay, so therefore the equation of QF is y is equal to minus a half x plus b. Now QF has the point 19, 1, so substitute that in. So when y is 1, we have 19. So that means b is equal to 1 plus 19 over 2. And therefore b looks like 21 over 2. So this equation is y is equal to, let's write it up here, y is equal to minus 1/2 x plus 21 over 2. And then finally, to find our h, it's the point of intersection, so we have to set them equal to each other. So x is equal to minus 1/2 x plus 21 over 2. Okay, this will be 3 over 2x is equal to 21 over 2. Therefore, 3x is 21, and therefore x is 7. And then since y is equal to x, y is also 7. So the coordinates of h are 7, 7. All right. D. Determine which of G and H is closest to the origin. All right. Which is closest to the origin? Well, H is 7, 7, and G is 9, 5, right? We figured that out previously. And we have to figure out which one of these is closest to the origin. Okay, well, that's just the distance from these to 0, 0. The origin is 0, 0. And they just use the distance formula. So the distance formula for the first one would be 7 minus 0 squared plus 7 minus 0 squared, all under the square root sign. And that looks like 49, 49, 98, so root 98. Distance formula on the second one, very similar. 9 minus 0 squared plus 5 minus 0 squared. And that's going to be what? 81 plus 25, which is 106. So obviously the shortest distance is this one. So H is closer to the origin than G. Suppose that f and g are functions. We say that the real number c is a real fixed point of f if f at c is equal to c. We say that f and g commute if f at g at x is equal to g at f at x for all real numbers x. Part A. If f at x is equal to x squared minus 2, determine all real fixed points of f. So, according to the definition in the question, f at c would have to equal c, right? It's right up there. If there is a real number c, if we say that the real number c is a real fixed point of f if f at c is equal to c. So that's what they're saying. And therefore, if we take this equation, that would mean that f at c which is equal to c squared minus 2 is equal to c. So if we take this part, c squared minus 2 is equal to c. Put everything on one side. C squared minus c minus 2 is equal to 0. And I think this factors pretty well. C2 1 minus plus. Yeah. So therefore c is equal to 2 or negative 1. And these, by definition, are the real fixed points. And that's it for part A. Move up to point B. Determine all cubic polynomials g that commute with f if f at x is equal to x squared minus 2. So by definition, the g and f functions commute if they hold the following property, that f at g at x is equal to g at f at x. If that's true, then this means that g and f commute with each other, this word commute. Now they're saying, though, that g is a cubic polynomial. Cubic meaning there has to have an x to the power of 3. So g at x has to have an x to the power of 3 with some coefficient. And of course a cannot be 0, otherwise it wouldn't be a cubic. And then some b at x squared, and then I won't use c, I'll use d at x plus e. So the function g has to be of that form. Okay, we have to now proceed with this. So f at g at x is this guy, so you put it in there. And then if you recall, f at x was equal to x squared minus 2. So that's what you would do. Whatever's inside, you would put it in x squared minus 2, which is what that is. And then you expand, and when you get expand, you get this big long expression. Then you collect like terms. So you have the coefficient in front of x to the power of 6, coefficient in front of x to the power of 5, x to the power of 4, 3, 2, 1, and then x to the power of 0. In a very similar way, you do g at f at x. F at x is this, so that goes into the bracket. And then you substitute what's in the bracket into this expression. So it'd be ax to the power of 3, but what's going to be to the power of 3 is what's inside this bracket here. So that's what that is. And then similarly, b x squared, but x this time is x squared minus 2, so that's what you put in there. And similarly, dx, where this is x. Then you expand that all out and collect like terms. Now, since this is equal to that, according to our definition, we have to now equate those two. This is equal to this. Now, what that really means is you have to compare coefficients. So, for x to the power of 6, my coefficient is a squared up here. And here, it's a. So that means a squared is equal to a. For x to the power of 5, we compare coefficients. Here, it's 2ab. And here, it is minus 6. Actually, there is none. Oh, I got to be careful. It's 0, because there is no x to the power of 5. X to the power of 4 coefficient. Up here, it's b squared plus 2ad. And then here, minus 6a plus b. X to the power of 3 up there is 2ae plus 2bd. And then in this bottom one, there is none, so it's 0. X squared up there is d squared plus 2be. And here it's 12a minus 4b plus d. And then the x coefficient up there is 2de. And then down there isn't any, so it's 0. And then finally, the x to the power of 0 coefficient up there is e squared minus 2. And downstairs, it's minus 8a plus 4b minus 2d plus e. Okay, great. Okay, so now we got to solve these. We got to get the actual values of a, b, and c. And then once we do, we can figure out what is that polynomial. So let's do that. And remember, I'll just write it here. G at x is equal to ax cubed plus bx plus bx squared plus dx plus e. And a cannot be 0. All right. So from this guy, from 1, a squared minus a squared equals a. So a squared minus a is equal to 0. Factor out the a, and we get a minus 1. So therefore, a is equal to 0 or 1, but a can only be 1 because a cannot be 0. All right, great. We got the value for a. Let's see, where can we go next? Let's go to this guy. From 2, we can figure out that 2 times ab is 0. But a we just figured out was 1, so let's substitute that in. So that means b must be 0. Okay, great. We got 2. Where do I want to go next? Let's try this one here. I think this should be helpful. 3 tells me that b squared plus 2ad is equal to minus 6a plus b. So b is 0, and then a is 1, and then this is 1, and b is 0. So this leaves me with that d is negative 3. And then I think the only other coefficient I need is e, and I can use, let's see here, which one should I use? I can use this one here, this equation. So that one tells me that 2 times de is 0. 2 times negative 3 times e is 0. Well, e is just 0 then. Okay, great. So a is 1, b is 0, d is negative 3, e is 0. So substituting them into here, that means g at x is equal to x to the power 3 minus 3x. Yeah, that's it. And therefore, that is the cubic polynomial. Let's go back to the question. It is the cubic polynomial g that commutes with f. Part B, or Part C rather. Part C says, suppose that p and q are real valued functions that commute. If 2 times q at p at x to the power of 4 plus 2 is equal to p at x to the power of 4 plus p at x to the power of 3 for all real numbers x, prove that q has no real fixed points. Okay. All right, so we have to prove this, but they're saying that it has no fixed points. Okay, so I think we can prove by contradiction. So first let's make an assumption, original assumption, that q at x has a real fixed point. And by definition, that would mean that q at c equals c. If it does, this would be true. And then we're going to show that this assumption is incorrect, and that means that q has no real fixed points. Okay, so here we go. They told me that p and q commute. So if that's the case, based on our definition, if p and q commute, then that means that p at q at x is equal to q at p at x, like that. And let's just put in c's since we are used to c's. So p at q at c is equal to q at p at c, like that. Now from this, we can put, instead of this q at c, it's equal to c, so just put in c. So there we go. And this basically is about as far as I can go, so I will just call that equation 1. Now let's revisit that big expression. That 2 times q at p at, and I'm going to use c's, to the power of 4 plus 2 is equal to p at c to the power of 4 plus p at c to the power of 3. Okay. Instead of this, I'm going to substitute, instead of, this whole thing, I will substitute this because it's equal. So that becomes 2 to the p at c to the power of 4 plus 2, and this side remains unchanged for now, like that. Okay, let's put everything on one side, and when I do, I get p at c to the power of 4 minus p at c to the power of 3, and that equals minus 2. All right, so this is my equation that I have to work with. I have to show, is this possible or not? If it's possible, then my original assumption is correct. If it's not possible, then my original assumption is incorrect. So is this possible? Okay, let's see. So we got to look at some scenarios, but just to make it a little bit more digestible, I'm just going to call p at c equal to a. So that reduces this to just a to the power of 4 minus a to the power of 3 is equal to negative 2. Is this possible? It's a little bit, I think, easier on the eyes. Okay, and I think I've got a few scenarios here. I think I have 3 scenarios. Okay, and I think those 3 scenarios should be sufficient. All right, so here we go. Okay. So first scenario, we're trying to prove this. Is this possible or not? And that is if a is greater than or equal to 1. If a is greater than or equal to 1, that means that a to the power of 4 is greater than a to the power of 3, right? Like, for example, if a was 3, obviously a to the power of 4 would be greater than a to the power of 3. So that means a to the power of 4 minus a to the power of 3 would be greater than 0. That means that a to the power of 4 minus a to the power of 3 could never be equal to negative 2 because it has to be greater than 0. Okay, so we proved that in this scenario it's not possible. What about if a is, we did greater than 1. How about if we do between 1 and 0? So for example, if you have a half, if a is equal to a half, what happens then? Okay, well, obviously a to the power of 4 would be greater than 0, but a to the power of 3 would be less than 1, right? Because it's a fraction. So that means that a to the power of 4 let's just use our example, 1 over 16. A to the power of 3 is 1 over 8. So a to the power of 4 minus a to the power of 3, in our example, is 1 over 16 minus 1 over 8, which is, if we do this, this would be minus 1 over 16. So regardless of what value you choose for a, you will find that this number will always be greater than negative 1. You'll never be able to make it less than negative 1. So since we're trying to show that it could be negative 2, it cannot be negative 2. So in this scenario, again, it would not be possible. The final scenario is when a is less than or equal to 0. So for example, a equals negative 1. In that case, a to the power of 4 would be positive, but a to the power of 3 would be negative. So therefore, a to the power of 4 minus a to the power of 3 would essentially be a positive number, correct? For example, this would be 1, and this would be minus 1, which is 2. And obviously that's greater than 0. So because that's greater than 0, it could never be negative 2. So in all three scenarios, we showed that a to the power of 4 minus a to the power of 3 cannot be negative 2. So therefore, our original assumption is incorrect. And that basically means that q at x cannot have a real fixed point. And that completes the proof. For each positive integer n, define f at n to be the smallest positive integer s for which 1 plus 2 plus 3 until s minus 1 plus s is divisible by n. For example, f at 5 is equal to 4 because 1 plus 2 plus 3 plus 4 is divisible by 5, and none of 1, 1 plus 2, or 1 plus 2 plus 3 is divisible by 5. Determine all positive integers a for which f at a is equal to 8. First, let's try to understand this question. They're saying that f at 5 is equal to 4, right? And what that means is that 1 plus 2 plus 3 plus 4, which is equal to 10, and 10 is divisible by 5. Okay, so by that same logic, if we have f at a is equal to 8, just copying that, it would mean that 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8, which is 36, and 36 is divisible by 8. So we have to figure out what is a. Well, 36, it's pretty easy to figure out the divisors. The divisors of 36, let's see here, we've got 1, 2, 3, 4, 6, 9, 12, 18, and 36. So these are the divisors of 36. Now, you say, well, is that it? Is the question over? These are the possible values of a? Well, it's not that simple, and I'll explain why. So let's work with this one by one to see why only some of these values are actually going to satisfy that while others don't. And that's what I'll try to explain. Let's say I choose my first one, this one right here, and I say I think that a could be 1. Let's see if this works. If a is 1, that means that f at 1 is equal to 8. Right there. So let's see if this works. By definition, that means that 1 plus 2 plus 3 until 8, which equals 36, right? And 36 is divisible by 1. Is that true? Sure. So that's good. But here's the key. This must be the smallest possible number for which this holds true. If we find a number that's lower, then this is not valid. So let's see. My assumption is that it's not going to work because f at 1 is probably going to be equal to 7 also. If that's the case, that means that 1 plus 2 plus 3 until 7 is equal, which is equal to 28, and 28 is divisible by 1. That's true. So since that's true, 8 is not the smallest, because remember, it's only true if that is the smallest. So since this must be the smallest, this must be the smallest value for which this holds true, and we've found a smaller value, f at 1 cannot equal 8. So f at 1 does not equal 8. So this one is no good. So you get the hang of it, hopefully. It's a little abstract, but hopefully you can understand it. Okay, let's try a equals 2, the next guy. If a is 2, that means we are essentially saying that f at 2 is equal to 8. Okay? So that means 1 plus 2 plus 3 dot 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 until 8, which is 36. And 36 must be divisible by 2. And it is. But what about if we try to say f at 2 equals 7? If it holds true, then this falls apart. Well, f at 2 equals 7 means that 1 plus 2 plus 3 dot 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 plus 7, which is equal to 28. And is 28 divisible by 2? Yes, it is. So that basically means that we found a smaller value, and therefore f at 2 also does not equal 8. So I will let you do the same thing for 3, 4, and 6. Same kind of story. Now let's move ahead to these guys. These are the ones where things start to happen for us. F at 9. Is f at 9 equal to 8? Well, let's see. If that's true, then 1 plus 2 dot 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 until 8, which is 36. 36 must be divisible by 9, and that is true. But can we find a lower number? Like, for example, can f at 9 can f at 9 equal 7? Or can f at 9 equal anything, really, lower than? Well, that would mean that 1 plus 2 plus 3 dot 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 all 7, which is 28. And then 28 would have to be divisible by 9. Is it? No, it's not. So we are good, but we still have to test all the other ones. We have to test f at 9 equal to 6, f at 9 equal to 5, f at 9 equal to 4, and f at 9, let's move this up a bit, f at 9 equal to 3, f at 9 equal to 2, and f at 9 equal to 1. Well, if f at 9 is equal to 6, that means that 1 plus 2 plus 3 plus 4 plus 5 plus 6 is divisible by 9. That sum is 21. 21 divisible by 9? No. And then similarly, this sum, 1 plus 2 plus 3 plus 4 plus 5, would have to be divisible by 9. Is 15 divisible by 9? No. Okay. This one, 1 plus 2 plus 3 plus 4, which is 10. Is it divisible by 9? No. This one is 6. Is it divisible by 9? No. This is 1 plus 2, which is 3. Is it divisible by 9? No. And this is just 1. Is 1 divisible by 9? No. Okay. So we exhausted everything, and we can conclude that yes, f at 9 is indeed equal to 8, because that's the smallest number. All the other ones failed. And in a very similar way, you can show this is also the case. And I'll let you do those. I mean, it's the same thing. I don't think you need to hear me go through every single one. And f at 36 is also equal to 8. So these are the only ones that hold valid. So the values of a, for which f at a is equal to 8, are a equal to 9, 12, 18, and 36.